seconds. Thank you so much. Okay. So when I was a student here, actually here, literally across the street at Harvard, so at some point I realized I wanted to do combinatorics, so I went to MIT, went to talk to Richard, and Richard gave me a paper to read. Well, this one, well, no, it wasn't this one, I'm kidding. But this paper is a paper that many of us have read, or at least parts of it, because it has all the major open problems in algebraic combinatorics. And problem 10 of that paper is to find the combinatorial, positive combinatorial interpretation of the Kronecker coefficients. I will tell you what they are in a second. And so that problem actually appeared in so close to 90 years ago by Murnaghan. And he and Kirillov also asked about the reduced Kronecker coefficient. So what are the Kronecker coefficients? First of all, you all know Littlewood Richardson. Littlewood Richardson gives us the multiplicities of your reducible modules in the tensor product of two others for the general linear group. The same thing you can do for the symmetric group. The symmetric group should be easier, right? Well, so with the Littlewood Richardson, we do have a combinatorial interpretation in terms of the Littlewood Richardson tableau for the Kronecker coefficients. We know by that result of Murnaghan that the Littlewood Richardson show up as special cases of Kronecker coefficients. So it's already the problem is getting kind of inversely interesting. So then it's something for this SN is actually harder than something for the general linear group. And now it's late. Okay. So that prompted. I told you that there is a special case for the Littlewood Richardson coefficient that prompted the definition of this reduced Kronecker coefficients. When you take the first row of the partition, you add something and it let it grow to infinity. In that case, if alpha, beta, and gamma add up to the same size, then you get actually the Littlewood Richardson coefficients, and Kirillov defined this. So they are the reduced Kronecker coefficient, but he called them extended Littlewood Richardson coefficient. And that was the other major open problem of Kirillov from 2004. Where do they lie on the spectrum between the Littlewood Richardson and the Kronecker? And so I've talked a lot about Kronecker coefficients, and I'm pretty sure you're convinced already that they're pretty hard. So the reduced Kronecker coefficients turn out to be exactly at that end. And so this is our result from last year. Basically, it's just a formula. It's a formula that says that every Kronecker coefficient can be written as a reduced Kronecker coefficient if you modify your partitions by adding these three rectangles to your partition for the reduced. So there is color coding here. Blue is reduced and red is the original Kronecker coefficient. So that settles that problem. So tells that two open problems from the first page were the same. And they're on the wrong end of the spectrum, unfortunately. But it also tells that so all these properties that people were hoping for the reduced Kronecker coefficients, they fail because they already failed for the Kronecker. And how do we solve this? Well, when I was a graduate student, actually Richard didn't give me to read that paper, but he told me to read chapter 7. Chapter 7, I still work with symmetric functions, and if you do some right substitutions in symmetric functions, you will realize that there are some identities you can write for the Kronecker coefficients using Schur functions. That you can add the right sizes of rows and long rows and boxes so that actually the Kronecker coefficient is preserved. So there is this identity. And actually the hard part here is to get the reduced Kronecker, you're supposed to be adding a long first row. The hard part was to show that when you add a long first row to a situation that fits in here, the Kronecker coefficient stabilizes. And how did we do this? Well, that actually is a reference to Peter Winkler's talk, We did 3D contingency array, so in his case it was 2D diagrams. We did in 3 dimensions. You can write the Kronecker coefficient as a signed sum over counting point configurations in 3D. Pictures like that. And if you have the right marginals, you can actually figure out exactly what's happening on the sides and remove some of the sides so you get an identity, an identity that looks like that, and then you get the Kronecker coefficient is the same where you add along first row, which gives you the reduced Kronecker coefficient. That's it.
Right, so in the next few minutes, I'm going to share with you a question I have related to concept and particles that I'm interested in and some thoughts and related work I have had. So start with some very basic concepts that hopefully most of you are already familiar with. The first one is ON, which is the concept on order set partitions of bracket N, and order is defined by emergent blocks. So here's just a picture of all 3, including all those order set partitions of the set 1, 2, 3. And the second concept is VN, which is the concept on all valid brackets of the product of 1, 2, 3 to N. And ordering is defined by removing brackets. And I also include a small picture of B4 here, which includes all the 11 different ways to get bracket around the products 1, 2, 3, 4. So the third concept you're going to see in a few seconds is defined using these 2 concepts. And this is defined by Kaplanov, and the point is a hybrid between these first 2 concepts you just saw. So here is the details. The elements of this new concept Kn are order set partitions of N with brackets. So here is example for N equal to 8. You just take an order set partition of A and the product and put some brackets around it. And the ordering is defined using removing brackets and all merging blocks. So it's obvious, hopefully obvious that this concept is built using elements from the first concepts we saw. And this is the reason why Kaplan called this is a hybrid between ON and BN. However, note that this really is not a mathematical definition. So what I'm interested in is to make this formal. More specifically, if we're given a pair of concepts F and G, can we give a formal definition for a third concept to be considered to be a hybrid of this pair? And if so, whether there is a canonical way to do it. So in order to thinking of this question, let's start back thinking about a geometric aspect of these 3 concepts. In fact, all these 3 concepts are realizable, meaning that each of them is a phase concept of some particle. So this is here, ON is the phase concept of the cohesion, BN is the phase concept of an association, and finally, AN, Kaplan's concept is the post-phase concept of a particle, which he calls the association. And the reason he gave this name was because he foresees that it will be a hybrid between the cohesion and association. On the bottom of this slide, I'm including a picture of 2 different constructions of cohesion association obtained by Rainer Ziegler and Castillo and myself. So you can see that they look kind of different. However, we can, in the next slide, I'm going to offer you a way to thinking about this model in a way that actually both model fits into. So this is how I look at this. This is again a 3-dimensional picture. I have on the bottom picture, I have on the post-side level, I have O4, B4, hybrid to K4, and the top above them are their respective geometrical realization. Now, if I look at this picture of a 3-dimensional association, one way to see it is this can be understood as obtained from the first particle in the pair by replacing each of its vertices with a copy of the second particle in a pair. So this picture indicates me that maybe this is a way to define a hybrid between a pair of particles. And if I take this to be a way to thinking about hybrid particles, maybe I can use this as the approach to study the hybrid question of concepts, the hybrids of particles, and using the phase concept as a connection. So in the last 2 slides, I will just provide you 2 instances of hybrid structure arising exactly this way. The first one is a restatement of a known result in the literature. So if I start with P with a simple T-dimensional particle, I will consider its omnitruncation, which means you truncate all of its bases from the lowest dimension to its highest dimension. So, and again, here's the picture. If I start P here, what I get is this one. But now if I look at again, what I see that this particle is obtained from this particle by replacing each of its vertices with a lower dimensional procedure. And then I lower it down to the phase posat level. What I see is I should get hybrid, the phase posat of P together with OD with the phase posat of its omnitruncation. And it's a well-known result that the phase posat of omnitruncation particle is equal to the order complex of the phase posat of the origin particle. It is actually tell you that it's actually nice way, something nice without the literature give you a hybrid structure. So this is my last slide. I will just be very brief to tell you a hybrid model arising in my recent joint work with Federico Castillo. So when we consider, work is G is a finite reflection group, P is a particle satisfying certain embedding conditions, which I'm not going to tell you. And we're considering the G symmetrization of P. Simply you just do a reflection group of the P around and you take the convex call of all the copies. And then this construction allowed us to produce hybrid models versus in the particle level, and then we use the phase posat connection to get on the posat level. And we have some characterization to describe the phase posat of the symmetrization of P, which will give us some insights thinking about hybrid posat question in the set.
So I'm Ted or Taedong. I studied with Richard. I started with Richard in 2008 as its 58 student. I studied combinatorics. And since then, I didn't actually do much in terms of geographical location. So I those blue X's are my offices. That one of the one at the bottom is my actual office. The other one is my de facto office, which is Starbucks. The red circle is my office now. I work for Google research right now. I have a slightly unconventional career, but right now I'm working in machine learning, applying machine learning to genomics and biology and medicine, and praying for help for research of my name many times. So I'll be talking about genetics and machine learning for the next 5 minutes in the math conference. I guess one of the reasons why I'm working in this field is because I think genetics is a crucial component in understanding human health and biology. So in this one study, you can see like 30% of the human health and illness in the US can be due to genetic predisposition. So it's an important problem to solve, especially from kind of personalized medicine standpoints. And every single one of us has 6 billion nucleotides, like 3 billion from your father and 3 billion from your mother, in a single human genome. So it's a very big data. I feel like big data is a very interesting problem to I'll wait for 8 more seconds until it goes to the next page. So today I will very briefly talk about this particular type of genetic study called genome-wide association study. So consider this, like say, very common disease like asthma, which is sometimes called phenotype of an individual. And here each row is an individual. And as I said, each individual has different genetic composition, but actually they share a lot of their genetics. So you can see like that's very on one position, people have some different nucleotides there, and very two positions have different nucleotides. And in this very, very simplified for example, you can guess that maybe that variant 2 position has something to do with asthma because they share this specific type of pattern, and basically the genome-wide association study for GWAS is doing it in a large scale and trying to find association between like this disease and your genetic positions. So my group has been working on this GWAS in many different ways using either supervised or unsupervised machine learning, which are like two different types of machine learning if you are familiar with. So we study various types of diseases. The first one is about eye feature, and we generated a more accurate eye feature using machine learning, and then having a better GWAS or genome association study based on that. We also worked on machine learning based lung diseases, where we can correct some noisy labels in hospital records using spirometry data, which is a lung function test, and then we also worked on PPGs or ECGs. Those are related to cardiovascular disease. Special PPG you can get from like your Federico or Apple Watches, so you can use it that way. So I did want to show like one actual result from my research. So this is an actual plot from one of my papers. So this is a result of a GWAS. The x-axis is a genomic location in your chromosome. So you have chromosome 1 to 22. Sex chromosomes are excluded here, and these towers indicate the significance of the association. So it's at sort of negative log p-value. And basically, you see these towers because the genotypes close to each other are correlated, and you can actually find like one known biology, which is this TCF21 gene that's known to be associated with lung function. Actually, it has a name. It's called Manhattan plot. That's why I have this picture. But it looks like a Manhattan skyline. So that's like one knowledge about genetics research that you could take home today. Probably unexpected. So my team worked on a bunch of different things. We had this project with an actual sequencing company called PacBio, and they decided to embed our software in their actual machine. So every time people run this particular type of machine called PacBio review machine, it runs our software. We worked on like accurately determining these genetic variants with tools called variant. It won some awards from it won some competitions that was hosted by NIST and FDA. We worked on some other projects like machine learning based association studies or fundamental machine learning issues. If you want to connect with me, you can.
Celebrate Richard's birthday. I want to thank the organizers, and I also want to thank the organizers of Richard's 70th birthday party. I was there for one day, and I particularly want to thank Trisha Hirsch, I don't know if she's here, and Vic Reiner, who's here somewhere, because they were instrumental in nudging me back into research. And of course, thank you to Richard for all his support and encouragement. So this is a story about two characters that I think we know, introduction to H2 and E2. I'm defining this symmetry function. It's an alternating sum. And my conjecture is that when m is even, the alternating sum is actually short positive. So I made this conjecture. It was actually in 2018, and it somehow found its way into Richard's supplementary problems, which I've forgotten about. But anyway, here's a list. You can see that for odd n, so the HE2n plus 1, for instance, is definitely not true positive. The sign representation shows that with multiplicity minus 1. For even n, HE2 is already a little interesting because there are a couple of different ways of writing it to show true positive, besides the force state, of course. And there are some linear relations here. I checked all this. Because for people who don't know, I checked all this with John Stembridge's SF package in Maple a long time ago, up to n equals 20. And then last week, I was very proud, I did it in Sage, and it went up to n equals 24. So, So where did this come from? I was actually trying to prove a different conjecture about short positivity of power sums in an interval when you take reverse slice order. I'm not going to say anything about that. There are a couple of different ways to rewrite HE2N. For instance, this way, you can see that the character values are nice, they're positive. The recursion is interesting. It gives you, again, a tantalizingly nice but not true positive generating function. And the interesting fact is when you multiply by H2 plus D2, you get something that looks like it's going to be a very simple module. So my idea was to try and rewrite this as an induced module, or maybe construct an algebraic complex. I have a lot of wild ideas that I never get to work. But yeah, so this is basically, as you haven't already guessed, to talk about the things that I tried that didn't work. Okay, so H2 to the M plus E2 to the M is actually the characteristic of a very simple transitive permutation representation. You take the subgroup GM in the symmetric group S2M that's generated by even products of disjoint consecutive transpositions. But the thing is, the thing that I want to do is when M is odd, I'd like to, quote, factor this in a different way as an induced module. I tried in the group algebra too, and I couldn't really see how to do it. And this is easy to do, the proposition, but it's the factoring that's hard, but M is odd. I thought I would. Okay. Let's see. Okay, yes. So people talked about Q analogs. So now there's a Q analog. These are the LLT polynomials. I'm not really going to tell you what they are if you're faster than me. So V is the vertical domino and H is the horizontal domino. So LLT polynomials are Q analogs of products of short functions. So if you take LLT for n minus k h's and k v's, you get exactly h to the n minus k, e to the k. I wrote out a few of them, again, if you can read very quickly. And if you take the alternating sum, this is the HE2 analog. You can see it's short positive, and the coefficients are positive polynomials that are positive in Q. This was actually an idea of Jae-Seong Oh, who is sorry that he couldn't be here, but he's here vicariously. So I met Jae-Seong at the OPAC conference in 2022. He came up to me and said, I saw your conjecture, and I said, what conjecture? Where? So he told me it was in the supplementary problems. And then he said, I think it's going to work for LLTs. Of course, I said, what are LLTs? But he sat down and ran some code, and he said it was Foster Tong's code. And sure enough, it seems to work. So this is the case when n equals 4 for h equals 4. So again, if you put q equals 1, you'll get my conjecture. Yeah, and so the q analog of the conjecture is that if n is even, this alternating sum of LLT polynomials is sure positive with coefficients that are themselves polynomials in Q that are positive.
So my career has had a bunch of ups and downs. It's maybe more checkered than some other people's. And it turns out that whenever my career is doing its best, its most up is when I'm studying downs and ups. So in my thesis, I did this looking at down and up operators in Young's lattice. And it's cut off there because I haven't hit bottom yet. Just as Richard showing us, what happens when the ups and downs come at you a little bit faster than you think. And all of this, what I'll talk about here is joint work with Darian Greenberg and May who are here, so you can talk to them about this. And Stefan Wagner, I'm kind of busy. Right, and I promised that I would do dance steps whenever I had extra time. Oh, I have lots of extra time. What should I say? Oh, it's dedicated to the hip, trendy rascal at Shipyard Central. So consider the Weil algebra. We've got two generators deemed. If you don't know what it is, that's fine. And there's one relation, du minus ud equals the identity. So my identity is shaped by du minus ud. It acts faithfully on the polynomial ring over for field of characteristic 0. If you set d to be taking the derivative and u to be multiplication by x, then that's exactly the relation you get. And we're going to call two words, as in monoid words, in this Weil equivalent if they represent the same operator. If up to that relation, they represent the same element. And so it's a theorem that we think goes back to Dixon-Yeh, if not earlier, that two balanced words commute. A balanced word is one that has the same number of d's and u's. But at one of these musicales, like the one last night that Clara Chen was hosting, Richard asked me these questions. How can you tell if two words are Weil equivalent? How many Weil equivalence classes are there of the given length n? And is it true that any two Weil equivalence words can be transformed one into the other by interchangings of these things, of adjacent balanced word swaps? So like we had du ud equals ud du, and that's just swapping du and ud. So the main theorem is that this is true. All these things are equivalent, that Weil equivalence of words is the same as some of these things were known, but some of these are new. And our main thing is that you can do them by a sequence of balanced commutations where you switch balanced subwords x and y that are adjacent. And there's another thing that you can do where you have balanced flips. So what you're allowed to do is in the center of the word, you can take some substring and that's balanced, reverse the word and switch all the d's to u's and all the u's to d's. So all of those equivalence relations generate the same thing. Oh, I have 10 seconds left. So why do I go so fast at sometimes at others? Here we go, great. So here are the missing definitions from the previous slide. If you've got a word, really just think about this kind of lattice path. I'm told this shouldn't be called the big path and that Igor should be in charge of tracking down the history for us. But you can write down a polynomial that just says, what's the height of each point as you go 0, 1, 0, 1, 2, and so on. And so you have this kind of a Laurent series. And these are easily computed and they are invariant under balanced transformation. So it was a key part in the proof of how we did this, along with the normal form for Weil equivalence classes. So we have a way to do that, and that let us, so that was the key structural piece, and then that let us get the enumerative results. It'll show up on the next slide in about 1 second. No, 10 seconds, because I have the thing set up that way. Okay, so treeless Shesty is like this. Oh, then figure out a sync. So Weil equivalent words have the same number of d's and of u's. So if we let a of nk be the number of Weil equivalence classes of words that have k d's and then n minus k u's, it's not hard to see this symmetry. Richard had some conjectures that were phrased as recursions or as generating functions, but we were able to write down a fairly simple formula and even prove it in a straightforward way for these things, a formula for a of nk that then all the other conjectures could be derived from. And then there's, if you add all of these up to get the total number of equivalence classes, we were happy to find the formula that included both Fibonacci numbers and the Catalan number, and 1 plus the Catalan number. So yeah, pretty special. And we also had results for the sizes of equivalence classes, which are too long to write down. The margin was too small to contain. So the further directions we have is we can extend our results to multivariate Weil algebras. We have actually a partial extension to one of the other ups in my career, which is when I worked with Georgia Bankert on down-up algebras. Balanced words always commute, but with some choices of parameters, you can get more equivalences. And an enticing open problem is the question of what happens in characteristic P, where you have more things that are in the center, like u to the p and p to the p are now in the center. And there's some connections with Rook equivalents that we looked at it, and it's not so straightforward to go from one to the other. And if you think that everything we did can be derived from the theory of Rook polynomials, please point us specifically where you want us to look, because we've looked around and we've seen the connections, but we don't find this particular thing. So it's kind of amazing that Richard could pick out a problem, from this very well studied area that's interesting and accessible, and then he can tell me how to use a cal. Thank you.
Dear Richard, academic siblings, nibblings, and friends, this flagship of the family has been working for 2 decades as a cryptographer and wants to tell you all about joint work with Daniel J. Bernstein and others. In crypto, the time you take must be independent of any secrets, otherwise they leak. If you use Honer's method in the binary exponent in RSA, somebody can read off your secrets of an oscilloscope. Because square and multiply takes longer than just square, so cryptographers up to 2018 have used Bickle-Fermat's theorem, but that's super quadratic time, even with fast Fourier multiplications, and it was constant subquadratic time modular inverses. Here's a treatise on the 3,000-year-old extended GCD algorithm. Let's look at an example in F7 of X. And look at how your divisions usually divide a degree k plus 1 polynomial by a degree k1 with 2 subtractive stages and a remainder of degree k minus 1. Unfortunately, sometimes you skip a degree as a red line in the example. Now your putative divisor has a leading coefficient of 0. You have to test for it and check whether it happens or not because time constancy. So here's our aha moment. Let's call the modular polynomial the divisor. So it starts as higher degree. We test the dividend for lower degree and non-zero coefficients and do a conditional swap. Then always a subtraction.
Dance.
So let's take a look at the polynomial division upside down because we have earlier reversed them. We only keep track of the degree difference that we call delta. We always do a conditional swap, then a reduce and shift. We see that this results in a uniform translation of 2k of these division steps, or diff steps, as we say, to a degree difference k divided. Further, for k of these diff steps that are extended Bezout's coefficients, we can quickly do. Let's simultaneously look at an upside-down division of two-adic integers. Here we have a conditional negating swap and an enforced reduced step. Again, for k of those binary diff steps, we can compute Bezout's coefficients, which are binary fractions. Higher negation, because we want numbers to decrease faster, and we will see how this is a fraction of a Solomon division. So here's our two-adic divide, which is a sort of a Hansel division, but signed. So if f is odd and g over 2 to the e is odd, then the pigeonhole principle tells us that there's exactly one q, and that's qg over 2 to the e is congruent to f modulo 2 to the e plus 1. And we say q over 2 to the e is two-adic quotient, and define the f mod 2 g equals f minus qg over 2 to the e, which is more even than g. Well, now let R0 be a two-adic integer and R1 be an even one, let Ri plus 1 be the two-adic mod of the odd part of Ri minus 1 against Ri. So we have that this is a diff steps becomes a two-adic integers if you have count exactly how many steps there are, and we can compare these two. So for exactly 2n of these steps, where n is number of questions, you know that this completes a GCD. I won't tell you the proof. It's too complicated. Uses some combinatorics and enumerative steps. And for 3n steps, this binary GCD will complete, and where n is the bit length. So we can always do a GCD using these diff steps, and this can be done using a divide and conquer method because only the bottom coefficients or the bottom bits of the numbers, and there's a natural way to divide and conquer, and recursively we have an easy n times log n to the 2 plus epsilon algorithm. So the key thing is that you never need to read and signs, and that speeds up the algorithm so much that it doubles the speed of inversions in time constant computations. So this is currently being used by Chrome and Firefox and Bitcoin if you're lucky enough to own any. Anyway, that's it, and happy birthday, Richard.
So I arrived at MIT 1994. I had just turned 17. Didn't really know what I wanted to do with my life. I didn't know if I wanted to be a mathematician. One thing I knew is that I hated combinatorics. And that it was just way too hard for me. The first class that I took was this polyphonic seminar with Richard and with Ardila. That just completely shaped my mathematical path. It made me fall in love with combinatorics. And it made me, one thing that I'm very thankful to Richard for is that I think he has really shaped my taste in mathematics. So I think the way he convinced me is that he had these very, very simple statements that were just so alluring because you could tell that if something so simple was true, there must be a really beautiful structural thing happening underneath. So what I wanted to share is some questions that I have about theorems that I have proved, but I don't really understand, and I would love your help understanding. So this is my first mathematical theorem. The number of having circles of 2n plus 1 points is always n squared. So you have 2n plus 1 points in general positions, kind of put them at random in the plane, and you're looking for having circles. Each one of these is a having circle. So here you have, and having circle has to go through 3 of the points, and has to leave the other half inside and half outside of the circle. Simple enough. It's fun to prove that there exists one, or that there, to give a lower bound, and you expect that you would get bound. That's what usually happens with this kind of problem. The surprise is that the answer is exact. So for any general set of points, the answer is always n squared. I can prove it, but I've never really want to really understand what this is about. So I would really love to know, but okay, quiet. The second fact that has intrigued me for many years is that the matrix polytope of the complete graph K4 is self-2. So what this means, you take the complete graph for vertices, you take all the spanning trees, okay? And then for each spanning tree, if these edges are 1, 3, and 5, then you put a point B1 plus C3 plus C5. For the indicator vectors of the spanning trees, they make a cloud of points in 6-dimensional space, because there are 6 edges. They lie on a hyperplane of dimension 5. And I just computed the n vector once, and I just found that it was symmetric. And that's just not supposed to happen. And then I looked carefully, and I actually was able to show that they're linearly equivalent. So you take the polytope and its dual, where you take these things and turn them into inequalities, xi plus xj plus sk less than or equal to 1. You get the same polytope. Why is that? The third one is about topolonomials. It's about the topolonomial of the complete graph. If you plug in 1 comma negative 1, you get the number of alternating permutations. So I'll say briefly what this means, and then a brief update on this. The topolonomial is defined recursively in this beautiful way, where you take your graph and you delete or contract. And then the topolonomial here is the deletion plus the contraction. If you get some recurrence, it's mysterious why they give the same answer, but you always give the same answer no matter what order you do the contracted. When you get some polynomial x and y, you plug in 1 minus 1, you get the number of permutations that go up, down, up, down, down. I actually talked to Spencer Batman yesterday, who told me that it had been explained, and I didn't know this. So there's an explanation for graphs due to Ma and Le, and also due to Cherekin and Portico. But actually, when I think of this, I don't think of the complete graph, I think of the root system here. And I'm just curious what happens at 1 minus 1 for other matrices that are not graphs. The fourth fact that I have proved with a number of my undergraduate and master's students at SF State, that I don't fully understand, is that for the simply laced root system, the ones of type A, B, and E, and only for the simply laced ones, the eigenvalues of the Laplacian matrix are introduced. So what do I mean by this? You take the root polytope, a bunch of points in space, you take the convex hull that makes a polytope, and you look at the graph of that polytope, vertices and the edges. You make a matrix that's vertices by vertices, so roots by roots, and in the alpha beta you put a -1. This is the root polytope of a 3. So you put a -1 if they're neighbors, and you put a 0 if they're not neighbors, and the diagonal continues. The eigenvalues are always integers. We can find them, we can prove it, but I want to know why the one for EH should be in. In this slide, I just wanted to tell you a little bit about kind of my journey of my understanding Richard. So in 1994, I thought he was an incredibly serious person. In the 60th birthday conference, I thought that I confirmed that suspicion. But then I got to know him a lot better. And this was a week before his 70th birthday conference in Colombia, where my partner Maybe was helping him go on this adventure, where he decided that he wanted to rappel down the rainforest in Colombia. Maybe told me I was fearful that this was going to be the last words, because he said, "Okay, I have my 70th birthday conference next week. I hope I don't die with him." Thank you for being here.